Okay, so we will start now the first session of presentation by young researchers. So this is a new feature of the ALGA meeting. And Aaron told us a little bit about the history of the ALGA in this last 20 years. And since then, the ALGA group in Brazil has greatly increased. And we have a lot of young researchers and students working in the field. So this is actually a very good thing. And this is an opportunity, this presentation by young researchers is an opportunity for the community to know what these young people have been doing. So this is going to be we have 3 short presentations each session. And today we will start with Maral Mostafazadehfard. Sorry. And she will speak on an algebraic study over secant varieties of rational normal curve.
Okay. So first, let me thank organizers for managing such a good meeting. This is based on the joint work with Anurag Singh. I'm going to talk about the secant varieties of rational normal curve. And you know that the rational normal curve is a rational curve of degree n in projective space Pn, and sometimes can be thought as an image of the parameterized map from a projective map, projective line. And sometimes we are interested to see the implicit equations of this curve, which are coming from a matrix in this form. This is a 2 by n matrix. And all 2 by 2 minors giving us the implicit equation of this curve. And the question is about the secant varieties. We can see that the secant varieties also coming from the same structured matrix also, namely when we are thinking about the second secant variety of this curve in projective space Pn, actually it is given by the equations of all 3 by 3 minors of this kind of matrix. And in general, when we are working with the T secant variety of this curve in projective space, we have this structured matrix. As you can see, this is an anti-diagonal matrix and full symmetry. And you can see that all T plus 1 minors of this matrix is given, are given the secant variety of this curve, T secant variety. In general, we call this kind of matrices as an Hankel matrix. This is the Hankel matrix of size T by n. And the coordinate ring defined by the determinantal ideal is called Hankel ring for us. These Hankel rings are very famous and they have some nice properties. I will recall some of them. The first one is coming from the result of Grusson-Peskin in 1982, that they can show that actually the determinantal minors of this matrix doesn't depend on the size, but just depend on the summation of the number of rows and columns. And what we have also the height of this ideal, which is a prime ideal, is n minus t plus 1 in terms of the size of the matrix. So we have a dimension of this coordinate ring, and this ring is moreover is a normal domain and Cohen-Macaulay ring, and is never unique factorization domain. And it is just Gornashian in the case that we have a square matrices, and otherwise we don't have Gornashianness. So we get interested to work on these rings, and the first question that we want to answer was about the canonical module of these rings. Actually, we know that because we have a homomorphic image of a Gorenstein ring here, we have a regular ring, so the canonical module exists. And we know that because we are working with generically Gorenstein rings, so the canonical module actually is a canonical ideal. It means that it exists and it is contained in R. Generically Gorenstein means that any localization of R at the minimal primes is Gorenstein also. So the good point is that, okay, Hankel rings have canonical ideals, but the next question is that what is the canonical ideal of the Hankel up to the isomorphism at least. So just get this set up, we look at this sub-matrix of the Hankel matrix. This is a matrix coming from the first t minus 1 rows And we consider all the maximal minors of this submatrix, and we call it P-frac. And as a first result, we could show that actually for the Hankel rings, the second symbolic power of this P-frac is the canonical ideal of the ring string. It was very good, and we know that because R is a normal ring, and canonical module exists in a Cohen-Macaulay ring also, the canonical ideal is a divisorial ideal. So we know that the omega of R is a divisorial ideal. So it is an element of the divisor class group. So the next question is that, can we compute the order of the canonical ideal in a divisor class group? Why it is important? It is important because when we have a finite order for the canonical ideal, it means that we have a Q-Gornstein rings. Q-Gornstein rings actually are rings which the canonical ideal is has a finite, the canonical divisor actually has finite order, or it's a torsion element in this group, or one power of that is a principal ideal. And fortunately, we could show that actually Hankel rings are Q-Gornstein, or the order of the divisor, canonical divisor is finite here. So the next question was about the divisor class group itself. What is the divisor class group of this ring? We know that divisor class group can be defined for cruel rings, and especially Noetherian normal rings are cruel. So we can also talk about the divisor class group, and we could compute that the divisor class group of Hankel rings actually is generated by P-frac that I have introduced in the last slides. And this is exactly this finite group over Z, and that was very good. We know that the divisor class group can be taught as a measurement of how is the divergency of a ring to be a unique factorization domain. We know that the Hankel rings are not unique factorization domain, but they are not so far from to be, as we have a finite group here. So as the divisor class group has finite order, so we know that what is the anti-canonical divisor, and we get interested to study the anti-canonical cover of the ring. And why it is interesting? It is interesting because sometimes for study the singularity of the ring, we can study the singularity of the anti-canonical cover, and if we can show that the anti-canonical cover is Gornstein, actually they have the same singularity. Okay, just let me define the anti-canonical cover. The anti-canonical cover for a ring which is normal domain and has canonical ideal also, we denote the inverse of the canonical ideal as an I. So the symbolic race algebra defined by I is anti-canonical cover of R. For the first time, maybe it seems so strange to study the singularity of S instead of studying the singularity of R, because S is more complicated. But sometimes, no. Sometimes you get much more result in S instead of R. So we get interested to study this ring. And the first, maybe immediate corollary that we get is that because we have a Q-Gornstein ring, so S is a Noetherian ring. And by a result of Watanabe, we know that when we have a Noetherian anti-canonical cover, the anti-canonical cover is quasi-Gornstein. What does it mean? It means that the canonical ideal of S is S itself. But for showing that S is Gornstein itself, we need to show that S is a Cohen-Macaulay ring. So for showing that S is Cohen-Macaulay, we need to show that any component here are maximal Cohen-Macaulay module. It is a result of the Goto-Hermann-Nishida-Villameyer to show that when a symbolic race algebra can be a Cohen-Macaulay ring. This is a sufficient and necessary condition. So hopefully we could show that not only the canonical ideal, but all symbolic power of the canonical ideal are maximal Cohen-Macaulay R module, and so S is a Gornstein ring. So we can study the singularity of this as a singularity of the ring R also. And as a lateral result, we could also compute the multiplicity of all the symbolic power of the canonical ideal also. After that, we get interested to study the singularity, and first because by work of the Iguza, Kempf, and the others, the determinantal variety defined over the generic matrices have rational singularities. The first question was about the rational singularities. Okay, it was very natural to arise this question, how about the Hankel matrices? Do they have rational singularities? And for knowing this, the ring has rational singularity when, as a necessary condition, the ring is Cohen-Macaulay normal with negative A invariant. And we see that the Hankel rings are Cohen-Macaulay normal, and also the A invariant is A1 minus T, which is always negative. Okay, we have necessary condition, and we have tried some different methods, but finally, we think that, okay, maybe the result of the Carney-Smith in 1997 is a good result, that she shows that F rational rings have rational singularities. Instead in studying directly the rational singularities, we prefer to go to the characteristic P methods that was introduced for the first time by Hakaser and Hunicke in 1987 to 1919 for studying the singularity of a ring, maybe getting the questions from the algebraic geometry and introducing to the algebra, and just working with the algebraic tools and answer the questions and again translate to the algebraic geometry. Maybe if I have time, for example, when we have F regular rings, so this implies the F rational rings. This implies F pure rings, and this implies F injective rings. And we have these relations. In the case that ring is Gorenstein, they are equivalent, and in the case of rings are Gorenstein, they are equivalent. These are in commutative algebra, but we have the same relation for the Q Gorenstein normal rings at least. We have log terminal singularity that implies rational singularities. We have log canonical singularities. And here, Dubois singularities. And we have this relation also in the case of the Gorenstein. Can be back to the canonical or terminal singularities, and in the case that we have a normal Gorenstein varieties. So we have this actually translation between the commutative algebra and algebraic geometry. So we get to the characteristic P methods. In the characteristic P methods, first I define the definition. Let's start from the Frobenius power of an ideal. The Frobenius power of an ideal IQ, where from now Q is, it's better to say that the natural power of a P. P is a characteristic of the ring. And the ideal generated by all Frobenius power, all elements to the power of Frobenius power is called the Frobenius power of this ideal. And just as a notation, consider R circle as a complement of the union of elements in the coming from the minimal prime of R. Sometimes you can think about the regular elements, but this set is a bit bigger. And the tight closure of an ideal, which was introduced by Hakaser and Hunicke, is an ideal actually consisting with elements of R whose Frobenius power belongs to the Frobenius power of I, just up to a multiplication of one element in R circle. When I is equal to I star, we say that I is tightly closed. And we say that a ring is F rational if and only if all ideal generated by a system of parameters are tightly closed. But it is shown that if you find just one ideal, that suffices. And hopefully, we could show that actually Hankel rings are F rational. So by means of the theorem of Carney-Smith, it means that they have rational singularities in characteristic 0. After that, we get interested to study the F regularity, because we have a Q Gorenstein rings, and we get some promising calculation from the Macaulay 2 that it shows that all of the Hankel rings actually are F-regular. So what is the definition of the F-regularity? Actually, a ring is F-regular if all ideals of the rings are tightly closed, not just the ideals generated by a system of parameters. So, and we get interested to study because we can say something about the log terminal singularity also. And the first result that we get is that actually Hankel hypersurfaces are F-regular. And, but by studying the anti-canonical cover, we are really close to show that actually all of the Hankel rings are F-regular. This is a work actually in progress, and we hope to show this so soon. Thank you for your attention.